wondering where this unit of Henry has come from, it's from Joseph Henry, and the reason why I bring him up is he was in fact an American. He was the first director of the Smithsonian, the first president of the American Academy of Natural Science, and so he made also great contributions to the science that we're talking about. So now we're going to put the inductor in the circuit, and you can see it does in fact have this coil-like symbol. My resistor is just a jagged line back and forth. So the inductance can be interpreted as an opposition to the rate of change of current. So we can't just switch on the circuit and have current flowing. Once the circuit's complete, the current begins to increase, but only slowly through the inductor. Then as we start sending current through the inductor says, nope, I don't do that. That creates a magnetic field. I don't do that. So how fast this happens depends on, again, a time constant like we did for the capacitors, and this time it's L over R. Remember the time constant for capacitors was RC. And the current, maximum current is again from Ohm's law. That's just Ohm's law based on the resistor. So what's going to happen is we're going to start going through the circuit, and since there's no current, there's no voltage drop across the resistor, so the voltage drop there is about 0. That means to get back down, if this is charged to like 6 volts, then if the voltage drop across the resistor is 0 because there's no current, then this is also about 6 volts. So that means all the voltage drop must happen across the inductor for this type of circuit that is basically resisting the flow. So now we know the equations for the time constant for an inductor circuit and the maximum current. We'll always put these in line with the resistor so that when we do get to maximum current, we don't draw too much power. So the current starts out close to 0 and then reaches an asymptote. So it should be no surprise that we have a very similar equation to our charging capacitor. But what's being limited is the current. So the current starts out at 0, just like a charge would start out with 0 for capacitor. So, and it increases with time according to the time constant rules. Then the voltage starts out at a high number and then decreases over time, so that there's basically no voltage across the inductor, because once the magnetic field is established, it basically just becomes a wire, and so has very, very little voltage drop. And then as we're discharging, the current starts out very high because the inductor is trying to maintain the magnetic field as it's losing it. So it starts out with a very high current. That takes a lot of energy. So as that energy that's being held in that magnetic field dissipates, so does the current. And again, the voltage starts out very high because there is a lot of potential difference across the inductor when this current starts up, and that creates the potential difference that then falls off over time. So only one of the graphs has the 1 minus e to the negative t over tau, just like the capacitor. The 3 other graphs, and both graphs for discharging, have just the e to the negative t over tau. So what do different time constants look like? Well, basically the time constant gives us an idea of how fast or slow the circuit is. If we have a very small time constant of just 0.1 here, then the circuitry is going to react very quickly. There's going to be very little impedance in the inductor for current flow, so it's going to basically accept it in a relatively quick fashion. However, if we have a time constant that's 1 second, the circuit's a lot slower. It's going to take a lot longer to get to its steady state with ultimate values. So, and again, the key values are that at one time constant, so for a 1 second time constant, this is t is equal to tau at 1 second for this one, and then with our half a second one, we got the same exact value right there. So this is t is equal to 0.5, and this is t is equal to tau is 1, depending on how quick the circuit is. And then, so e to the negative 2 is 86.5%, and e to the negative 3 is way out here for this one, or here for this one, for 95%. Then if we look at the voltage going across, then this is a decreasing curve, a decreasing exponential. And so again, the quick circuit is going to do it quick, so the very A small time constant is going to do that very quickly, whereas when we get to a 1 second time constant, it's going to do a lot more slowly. And again, we have the same key values that at 1 second with the 1 second time constant. So this is t is equal to tau. We're at 36.7% because that's what e to the negative 1 is equal to. And then e to the negative 2, we're down at 13% of the maximum value. And at e to the negative 3, we're down at just 5% of the maximum value. Then we can look at the two together, the voltage and the current. So as the current's increasing, the voltage across the inductor is decreasing. Okay, so time for a problem is here we have an inductor. This is called an RL circuit because it has an R and an L in it. A circuit with a capacitor is called an RC circuit. This one's called an RL circuit. So we have a very large electromagnet, has an inductance of 16 Henry, so very, very large. The resistance of the winding is just 8 ohms because it's a very, very long wire. We'll treat the electromagnet is an ideal inductor in series with a resistor. Okay, so we have that in the diagram. When the switch is closed, we have 24 volts here. So 8 ohms and 16 Henries. We want to figure out what the ultimate current is and then how long after closing the switch does it take to get to 99%. The first thing we want to do is just find the maximum current from Ohm's law. So I max is equal to 24 volts divided by the resistance of the circuit, and that gives us 3.0 amps. So in reality, this is just one device, but when we're analyzing it with using our ideal inductors and our ideal resistors, we assume that a resistor doesn't have any inductance, and we assume that an ideal inductor doesn't have any resistance. So just like we took a battery and modeled it as an ideal battery with an internal resistance in order to get the behavior of a real battery, we're going to model an inductor as an ideal inductor, so having no resistance, and in series with an actual resistor that doesn't have any inductance. And this just makes our analysis easier as we're trying to figure out what's going on. So the moment the switch is closed, again, there is no current going through this, and so the voltage drop across the battery is 0, and all the voltage drop will need to be across the inductor. Now we're going to work on a little bit more challenging problem and figuring out at what time do we reach 99% of the maximum value. And how we do that is we're going to use the formula for current as a function of time. And again, since current is increasing, it's the 1 minus e to the negative t over tau. And so 99% of maximum value means I'm going to go multiply the maximum value times 0.99. So this says 99%, right? And we're going to set that equal to our function of time, t over tau. And I went ahead and calculated the time constant. It's just L over R, so it's 2 seconds. So we'll need that in this problem. So we got 0.99, and then this cancels out on both sides, equals 1 minus e to the negative t over tau. Then what we need to do is rearrange. So I'm going to bring the e over to the other side. I should do it this way. E to the negative t over tau equals 1 minus 0.99, so that's equal to 0.01. And how I undo an e is take the natural log of both sides. So I'm going to take the natural log of everything. That basically cancels out the e because natural log of e is just 1. And so I have negative t over tau, and it gets rid of the exponent as well. So it's basically whatever the exponent is, so x. That's more correct. Okay, so we take the natural log of 0.01, and that gives us 4.6, and it's a negative, not negative there, but it does turn out to be negative because we're taking the log of a number less than 1. So, and we know tau is 2, so therefore t is equal to, and these negative signs cancel out, and so we get 4.6 times 2 seconds, because that was our tau, is equal to 9.2 seconds. Now it's time for you to give it a try, and basically at one time constant, what are the values for the current and the voltage? Okay, hopefully you've gotten a chance to figure it out. Again, tau is 2 seconds. Not that it really matters for this problem, but we did figure out the maximum current is 3 amps. And so now we want to put in 1 minus e to the negative 1 because it's one time constant. Remember that this is one of our special values. That's 0.632. So that's 1.9 amps. And then our V volts maximum is just the volts supplied to the circuit. And again, this is e to the negative 1, which is one of our special values, and that's 0.368. So we get a maximum, so we get the voltage at that time is 8.8 volts. So if this is basically based on time constant, then instead of 10 amps, that's going to be 24. What we're going to do is then this at 1.9 amps is going to be about there. That's not 24, because that's 3. So 1.9 amps. And then here, this is 24 volts at one time constant is 36.8%. And so that would instead be 8.8 volts. There's all the values again.